ask you about one thing, but maybe we can do that next Monday. And that is to have this break a little shorter to allow to finish earlier, because I know there are quite some people from marine technology who want to be back at Tuholt at 10:15. So today we do it just, please remind me, say 5 minutes before to stop. So then we stop 5 to 10, if that is okay. If I forget it, please raise your hand, make me aware of it, so that you can get back to Tuholt. Regarding the exercise, we have it here, exercise 1, and to do that, you'll get the material in a minute. So it is a very simple problem, but you'll be a little bit surprised, I hope, when you do it. What we want to do is we want to make a numerical differentiation. We want to determine the derivative of tangent of x. And we want to just do it in one point, just at x. And we do that by varying the grid spacing, h. So, and we discussed that in a minute. Okay, so let us stop here and move on. The thing that is missing from the theory of PDEs is the concept of well-posedness. When is a problem, PDE problem, well posed? You know that? Okay, you get it. It's not just something mathematical, it's very important, especially for multiphase flow. We have a lot of multiphase models important for industrial applications which are ill-posed, so they cannot be used. So we need well-posed problems. Well-posed problem. And we say that a PDE problem, and by problem we mean the PDE including initial and boundary conditions, is called well-posed if we have three conditions: a solution to the PDE problem exists, and we have one, the solution to the PDE problem is unique, so that we have only one, that we can show that, and the solution, let's see if we can get it in here also, the solution to the PDE problem depends continuously on the initial and if we have just the boundary conditions, and it's just the boundary conditions, and we say boundary data. So if we have a boundary value problem, like for elliptic problems, we mean here then that the solution depends continuously on the boundary data. So that means if we change the boundary data a little bit, the solution will change a little bit. If we have an initial boundary value problem, for example for the parabolic problem, the heat equation, where we have two walls, we have a bar, and we have boundary conditions. This is time, this is x. Then we have boundary conditions here, and we have some initial condition. Then it means that the solution depends continuously on the initial conditions and the boundary conditions. That means if we change them a little bit, the solution will change a little bit. Why is that important? if we would have big changes, then we could not do it, because then any small change would give us a completely different solution. So then we would not be able to compute it, because in any computation we have errors. We will see that in a minute. We have by discretization, by round-off, by approximations of boundary conditions. And if we would have big changes, then these big changes would it make impossible to compute it, because once we get this solution and this solution depending on the small change, that is impossible. So we need a well-posed problem. The example for an ill-posed problem would be, that is coming from US, if a butterfly in Brazil would flap like this, if that would cause a hurricane in Texas, that problem would be ill-posed. A small change would cause a big change. So that we cannot have, and we have actually not. But for the models, we must make sure that this is true. We must make sure that we have a solution, that we have just one, because if we have two, we might get this or this, we don't know what we get. And we must have, as I just explained, dependence, a continuous dependence on initial and boundary conditions. So that is this concept that I want to make you aware of. So far then the theory, and now we want to enter the discretization, the numerical solution. And we do that by looking at the sources of error in CFD. That would be now chapter 3. That is a little bit different from the book. I take parts of it from the book. But we will get into more detail of chapter 3 in the book later on. Sources of error in computational fluid dynamics. In this course, we shall focus on the finite difference method. That's a well-established method, and you will see it is relatively easy to solve PDE problems. What we do there, we start very simple, also like in exercise 1. We look just at the case where we have differentiation. But if we have a PDE, then the derivatives in the PDE are approximated by finite differences. That is the idea. So, and if you think of it, the derivative is defined as a limit of a process. For example, you would define, say, if we have a function, we have a du dx, if we would define that at x, then we could do it that we have h, then we would say we have here u of x plus h minus u of x divided by h, right? That would be a possibility to define the first derivative with respect to x of a function u. So that would be, but what we do in the finite difference, we just use this formulation. So we replace that, we say that the du dx is approximately equal to this evaluation with a finite h. So we don't let h go to 0. We may have a small h, but it's finite. And by that we make an error. So we want now to learn about this, and we do that for an example. And the example is very similar to this, but in the example we assume that we have just given the values of u at discrete points. So what we do is we suppose that du dx should be computed, is to be computed in an interval 0, 1. What I do now is relevant for ODEs and PDEs. And we define first grid points. That are the points where we do the approximation. And for this interval, we would do it in the way that we say the grid point xj. So we take that with a subscript j is equal to this j, that is the integer number, j times, and we use here the notation delta x. And then we want to cover the whole interval, we let j go from 0, 1, and so on to a certain number of points, a number of intervals actually, nj, because we have nj plus 1 grid points, because we have also the 0 included. And in here, the delta x is the grid spacing. And if we have the interval 1, the length is 1, and we divide it by nj intervals. So that is called the grid spacing. So, and now we have different options to approximate the first derivative. But now, opposed to here, we assume, in this example, we assume that we know the function. Now we shall assume that we don't know it. So the first derivative of u with respect to x at the grid point xj can be approximated by following difference approximations. Now I'll give you 3. 2a, I use now the notation from the book. The notation is for a forward difference delta x uj. So the x is a subscript here, divided by the grid spacing delta x. So here x is a subscript. I'll write it even more clearly. It's a subscript, and it's defined by the forward difference, where we take uj plus 1 minus uj. So that is called the forward difference. And we can illustrate that easily. So if we assume that we have the x-axis here, and that we want to write the u up here. And now we assume that we have a couple of grid points. We say we are here at the grid point xj. Then this would be the grid point xj plus 1, and this the grid point xj minus 1. What we assume now is that we have just the values of u given at the grid points. We have only given them here. So this would be the uj, this would be the uj plus 1, this would be the uj minus 1. That is the common situation that we have with the PDEs. We have initial conditions, boundary conditions, and we We know it at some point. We have approximations, but only at the grid points. Now, what does that mean? It means that, let's see, some color. It means, in this case, that we approximate the slope by the forward difference. What is this? Here we take this here. So this is then the slope that we use, that we get when we use this approximation. So then we say, okay, we approximate the slope by this finite difference, given by the slope from xj to xj plus 1 with these approximations of u. So that's one option. We can do differently. That would be 2b. Instead of taking a step forward, we could take a step backward. And that is to give us then the backward difference. The notation is this, also with a subscript x here, as is the operator, backward operator, operating on uj, divided by the grid spacing delta x. And the backward operator takes uj minus uj minus 1. That is the backward. That is then the forward. We have now the backward difference. So in this case, we would then use uj and uj minus 1. So let's see. So then we would use this here. So then that would be our approximation. So that is then the forward difference, and this is the backward difference. And then you can imagine if we just take the average, or if we take, let's see, is it the average? Yes, if we take average of those, we would get the central difference. That, so I write it here, then you can see it better. And the central difference we can express with the operators from the book. That's a central difference operator. I'll define that in a minute. And that is an average operator, uj divided by delta x. What it comes down to is that we have here the uj plus 1 minus the uj minus 1 divided by 2 delta x. And that is the central difference. What do we do in that case? Let's see if you can see that. We take this and this. See it, that would be the central difference operator. So then the slope would be this. What we want to approximate is the first derivative, which is the slope at this point. So we have three options in this. We can continue to have many more if we take more points into account. So then we have three possibilities. We limit ourselves to that. Just to complete this notation here, in this notation we have been using that uj is an approximation of the exact function value. So that is, so uj, that is uj approximates, or is an approximation the exact value of u of xj. So if we use this notation, we want to have then the convention that if we use these index notation uj, that we have an approximation, in that case at the grid point xj. And if we have it u of xj, then we assume it is exact. And the notation that we have been using here, this difference notation, the mu x of uj, that is the so-called average operator, is formally defined in this way, by these half indices. And so that is an average operator. So if we would use that first, then we would get this here. And the delta x, if we would operate that on, sorry, it is a subscript. Both cases is a subscript uj. That would be the difference, the central difference operator, defined with half indices. So that is the, I'll call it here the basic central difference operator. So if you apply this behind each other, it says, so we have, if we would not apply to uj but to this, then it would mean that we have to raise the index by 1/2. Then we would get here uj plus 1 plus uj minus, and then we would again apply the rule that we would take this with an index back. Then we would have minus uj plus uj minus 1. So this is an index notation. That makes the notation a little more compact. So we have, what we see here, we have different options how we can approximate the first derivative of the slope, by forward, backward, or central difference. Now we want to analyze that, and we want to find out, when we do this with PDEs, with partial differential equations, what will be the consequence when we do that. And then we get, of course, errors, because as we saw in the beginning, when we use the definition of a derivative, we do not go with the limit h to 0, we stop at some point, because we can only represent finite numbers on the computer. So, and the first error that we shall now look at is the truncation. That is due to the fact that we do the approximation with a finite h, with a finite, or with a finite grid spacing delta x. And the truncation error of the finite difference method, in our case we had just looked at the ones that forward, backward, and central, these are these ones, that can be evaluated by inserting the exact function values. And that is u of xj. So now we assume that we have some known function u of x, then we take that at the grid point xj, and we do that by assuming that we have a smooth function. U of x, and we do then the replacement for be what originally we have been using as an approximation, uj. So we test essentially how will the difference approximation handle an exact solution if we put in the exact solution u of xj in the place of uj. And then we compute, computing the following, and we see how the truncation error is defined. That will allow us to assess, to evaluate the accuracy of the difference operators. So we do it for the three difference approximations. I use now this notation for truncation error. Truncation error is dependent on the point, and it is dependent on the grid spacing, delta x. So we replace then the uj plus 1 by the exact function value of u at xj plus 1. So that is at the grid point xj plus 1. Minus u of xj, that is uj replaced by the exact function value u of xj, divided by delta x. So that is what we mean by inserting the exact solution, the exact function value u of xj for uj. We have it done here for xj and here for xj plus 1. And then the truncation error is defined, what we get out of that, compared to the exact derivative, which is the du of xj dx. So that is now assumed that we know that, because we know the function u. And in a similar way, we can do that also for the other difference operators. That was for the forward. Now we do it for the backward one. The notation is similar, but here we had uj minus uj minus 1. So that will give us u of xj minus u of xj minus 1. And we subtract the exact derivative. And similarly for the central difference operator, we have then u of xj plus 1 minus u of xj minus 1 divided now with here 2 delta x. And then we take that, subtract the exact derivative. So that is how the truncation error is then defined for our difference approximations. Please note, in the textbook by Plescher, Penhill, and Anderson, Plescher and L, they use the following notation. They use T, E, and in my notation that would be minus T. So I have approximation minus exact, and they have exact minus approximation. So that's the only difference. But I prefer this because this is more common in numerical analysis and also in other CFD books. So, the question is, how can we evaluate now the truncation error? If we have defined it by looking at the approximation of the exact function and relate that to the exact derivative, well, we remember basic calculus. What can we do here? Any suggestion? First, maybe I'll give you a hint. The xj plus or minus 1 can be expressed as xj plus minus delta x. That is just a definition by the grid points. So that means the u of xj plus 1 is u of xj plus delta x. So what can we do? We know u, and we know it is smooth, we have all the derivatives. Any suggestion? So we can write this as u of xj plus delta x. And here we have u of xj. So we can relate everything to the point xj by using Taylor expansion. That is the point here. So we can use Taylor expansion of this here, that is of u of xj plus minus delta x, and we use that then around the point xj. That will be the point around which we do the expansion. Then we will have the following. We will have u of xj, let's first take it plus, or plus delta x. That will be u of xj plus delta x du of xj dx plus delta x squared half the second derivative of u of xj dx squared plus, we continue, we get the next one would be delta x to the power 3 divided by 3 faculty, that would be 6. Third derivative of u of xj dx 3 plus, and so on. Be able to continue. Sometimes we need to continue if we have higher order terms, otherwise we don't need that. We have here, if it's minus, we have here a minus, and we have here a minus. So then we have that. And then we can evaluate that by inserting it in here. So we insert now the Taylor expansion 4 into the different truncation error 3. And we get, we are skipping, that is all dependent on xj. So then we get for A, truncation error of the forward difference approximation will be, here we have then to use the plus. We get u plus delta x du dx plus delta x squared half d squared u dx squared plus higher order terms. That would represent the u of xj plus delta x. And then we get here minus u divided by delta x. What do we get but from that? The u cancels, and we can factorize the delta x, and from that we get delta x half the second derivative of u with respect to x plus higher order terms. And that we can do also for the others, and we can get from that that the truncation error depends on the first order of delta x. So that means if we do a grid refinement, then we see how the truncation error will decrease. So from that we see that will be 5a, that the truncation error for the forward difference operator is of the order delta x. And that means that we have order O of delta x means that the absolute value of the truncation error can be estimated by some constant times delta x. So essentially you could say that the truncation error is equal to this derivative essentially at the point xj. It's actually between xj and xj plus 1. But we can assume it is at xj times delta x half. Then the truncation error will go down to delta x. So if you halve the grid spacing, the truncation error will be halved. We get a similar approximation for the backward difference operator, but for the central difference operator, so we would get, I skip now the derivation because we're short of time, we get that this is second order. So that means that the truncation error goes down faster. If we halve the grid spacing for the forward or backward difference operator, the truncation error will be halved. But if we have here delta x half squared, it will have delta x squared by 4. So the truncation error is 1/4 of the truncation error of the grid spacing delta x. So this is more accurate. The central difference operator is more accurate. So that is what you can expect from the truncation error. And the error that you also have is the rounding error that is often overlooked in CFD and other disciplines, and that is due to finite precision. Of floating point arithmetic on computers, but also in MATLAB. Because if you have a number, you must represent it on the computer. For example, pi. You cannot represent pi exactly. That's a number that cannot be anyway. But even if we have a number with a lot of digits, the number of digits is limited that we have in arithmetic. And that causes errors in the representation of the numbers on the computer. If we have two numbers that are close to each other, we can have an error on both of them. If we take the difference, as we do, we get cancellation. The errors cancel, and we get something that we would not expect. That is due to rounding error. And that you will see in the exercise. Okay, so I think it's now time to stop to allow people from tutor to get there. So we have seen now two of them, truncation error and rounding error, and you will see that in exercise 1, doing the approximation of the first derivative of tangent of x. So we'll meet then on Monday, for most of you, at 12:15 in K26, and for the others at 18:15 here.